So, TRIACs. This is not intended as an introductory video. Instead, I want to delve into all the parameters you find in a TRIAC datasheet and how they affect a TRIAC's operation. So the whole thing might get quite long and I might have to split it into different parts. We will see. Anyway, here's a short recap to establish some terminology. So what I got on my breadboard is a TRIAC with its main terminal 1 and main terminal 2 and gate. Between main terminal 2 and main terminal 1, I have a simple loop here with my big power supply and my electronic load, card link, just some switches and light bulbs. I've only drawn in one switch and one light bulb. And between gate and main terminal 1, I have a loop here with a 9-volt battery, a momentary switch and a resistor just to limit the current that goes through the gate. Now, what can we do with that? So at the moment, my positive output of the power supply is connected to main terminal 2 and the positive of the battery is connected to main terminal 2. And if I take my momentary switch and give a short pulse to the gate, positive pulse, the TRIAC switches on. And it stays on until I break the circuit. Wonderful. But you can do more with the TRIAC. I mean, it's intended to switch AC. So I can basically reverse the polarity on my main terminal 2 and it works just the same. But there's more. I can also reverse the polarity on my gate. And it still works. And of course I can switch back the polarity on my main terminal 2 and it also works. So I ran that little circuit in 4 different configurations. Gate positive, main terminal 2 positive, gate positive, main terminal 2 negative, main terminal 2 negative, gate negative, and main terminal 2 positive and gate negative. Always in reference to main terminal 1. If you look at the TRIAC datasheet, all polarities are always referenced to main terminal 1. And that is usually expressed as running the TRIAC in 4 different quadrants. And they are usually numerated 1 counterclockwise, 2, 3, and 4. So a TRIAC is also called a 4-quadrant device. And in some literature, they call the quadrants a little bit different. They say quadrant 1 is 1 plus. Quadrant 2 is 1 minus. You have the plus and minus referring to the gate polarity, and quadrant, not quadrant, but 1 meaning that my main terminal 2 is positive. And accordingly, they call 3 minus, and 4 3 plus. I don't like that terminology, but it pops up at some places. And now I have to go into a little rant about some, let's say, misleading information you find on some introductory material about TRIACs on the internet. So there are several sites out there showing a picture similar to that one here, which I have drawn, stating that a TRIAC is behaving just like two reverse parallel thyristors, or SCRs. I will call them SCRs. Or even stating that this is the equivalent circuit, and they use the equivalent sign, to a TRIAC, which is absolute bullshit. Okay? If you look at that circuit here, if our main terminal 2 is positive, of course we have to trigger this SCR here. So we have to put in a positive pulse into the gate. Yeah, running that way. You remember our little circuit. You cannot switch on an SCR with a negative pulse, pulling something out of the gate. That's not working. If our main terminal 1 is negative, we would need a positive pulse, yeah, flowing here to main terminal 2. And remember, if our current source for the gate is connected here, this is bullshit. This is simply not working. They then go on and say, okay, this is a physical construction. So if you look at it on semiconductor layer of that circuit. And that's wrong too. I mean, this is that SCR, no problem. To be more exact, this is this P-gated SCR. So P and PN, and the gate is connected to the P layer. Well, if you turn that around just 180 degrees like they did with here with the SCRs, you immediately recognize that this is PN, but the gate is suddenly connected to N. So these two parts, they are not the same. They are not, it's simply wrong. And to correct that, we would have here what that is. That part exists, but it's an N-gated SCR. So there are SCRs. I don't know if they are even produced, but they existed, or they exist at least in theory, where the gate is connected on the anode side. And now, that makes a whole lot of more sense. I mean, this is equivalent to that, no problem. And that is kind of working. It's kind of working. I mean, if I connect some current source here to trigger my gate, okay, positive here. I put a positive current here through the gate back to main terminal 1. I switch that on. Now my main terminal 1 is positive and main terminal 2 is negative, so I need to switch that on. And the nice thing here is I trigger an N-gated SCR by sucking something out, giving it a negative pulse. So yeah, at least I could run that circuit, okay? I could run it. It's still not behaving exactly like a thyristor, because we've seen a thyristor works in 4 quadrants. That thing only works in 2 quadrants. But yeah, we can say it somehow leads to a thyristor. In a proper textbook you will find something like that. You already know that picture here, 2 reverse parallel SCRs, one P-gated, one N-gated. Yeah, that was our corrected version of that picture here. And the construction of these 2 SCRs on a semiconductor level. Now in the textbooks they will not state that this is the equivalent circuit of a TRIAC. They will state you can derive the TRIAC from that circuit, or you can derive the symbol of the TRIAC from that by simply pulling your 2 SCRs together. Likewise, they say from these semiconductor layers and how they are connected, you can derive somehow the internal construction of a TRIAC on a semiconductor layer level. I won't go into details here. There's a nice article on the English Wikipedia about TRIACs where they show how the current flows through the different semiconductor layers depending on in which quadrant you are running the thing. What you take away from that picture is that the internal construction of a TRIAC is highly asymmetric. Yeah, that will bite us later. Anyway, enough about introduction and recap and ranting. Let's have a look at some parameters in the datasheet. So I want to start out with all parameters related to gating, that is the gate, latching, that is getting the TRIAC from its off into its conductive on state, and holding, that is to hold the TRIAC in the on state. And the first 2 parameters here are the gate trigger current or threshold current and the gate trigger voltage or threshold voltage. If you look at our little circuit, of course there's a voltage drop between the gate and the main terminal 1 when we try to put some current in here. That's the gate trigger voltage. And we need to apply a minimum current into the gate or out of the gate. Yeah, it's 4 quadrant, yeah, plus minus always. And that's the gate trigger current. For the gate trigger current, we have 4 sets of parameters depending on in which quadrant we are operating the TRIAC. So T2 plus, that's, yeah, not main terminal, just terminal 2 plus, gate plus, T2 plus, G minus, etc. But these are our quadrants, 1, 2, 3, 4. And each time we get a different value. And you see, between quadrant 1, where we need typical 2.5 milliamps, and quadrant 4, where we need typical 11 milliamps, there's a factor of over 4. So it behaves really bad in quadrant 4 in regards to the gate trigger current. The gate trigger voltage is not so much dependent on the quadrant we are in, but it is very much dependent on the voltage VD, that is the voltage between the main terminal 2 and the main terminal 1 in the off state that is applied. And you see there is really at 12 volts, which I'm running it currently, it's a typical 0.7 volts. But for 400 volts across the TRIAC main terminals, it can be pushed down to 0.4 volts typical, or even minimum value of 0.25 volts. Let's measure these two extremes here between quadrant 1 and quadrant 4. And since these are static characteristics, it's completely okay to measure them with DC. We will come to AC, oscilloscope and function generators soon enough. So I wired up everything for quadrant 1, and instead of the momentary switch, I put in a potty so that I can change the gate current. You see, at the moment we have 1 milliamp gate current and 0.4 volts gate voltage, and nothing happens. If I increase that now, 1.1 milliamps, 1.2, 4.8 volts, 480 millivolts, 1.3, 530, 1.4, 560, 1.5, 0.6 volts. Oh, okay, let's call that 1.5 milliamps and 0.6 volts. And there's another effect I want to show you. We are at the 1.5 milliamps and 0.6 volts, but I have cut off my load circuit. If I switch the load circuit on, of course it latches, but the voltage across the gate makes a little jump from 0.6 to 0.7 volts. Let's try the whole thing in the fourth quadrant. That's quite easy. I just have to switch the polarity of my load side of the circuit. And we expect to need a whole lot more of trigger current. So we go up here. Yeah, 2 milliamps. 3, 4, 5, nothing happens. 6, 7, 8. Okay, 8 milliamps. Let's go back to, cut that off. Let's go back to 8 milliamps. Yeah, near enough. 7.7 volts at 8 milliamps. Oh, sorry, 0.77 volts. Let's say 0.8 volts. And now let's switch it on. And you see that? The jump on the gate voltage from 0.8 volts approximately to minus 0.4 volts. Yeah, that's interesting, huh? So we have indeed measured a big difference between the trigger current required for the first quadrant and the fourth quadrant. Not quite the typical values, but yeah, near enough. I mean, they are typical values. While the gate trigger voltage, typically 0.7 volts for our VD 12 volts, is, yeah, spot on with 0.6 volts and 0.8 volts in quadrant 1, respectively quadrant 4. However, as soon as the thing latched on, that is, got into its conductive state, in quadrant 1, our gate voltage made a little jump from 0.6 to 0.7 volts, while in quadrant 4, it made a huge jump from 0.8 volts to minus 0.4 volts. That's 1.2 volts negative. So if you are indeed using a resistor here to limit your gate current, yeah, and you expect, okay, I dimension that thing according to the voltage I have here available and the voltage drop I'm expecting here. If we are in quadrant 4, my voltage drop here in our example changed in the negative direction by minus 1.2 volts. That is, if I'm driving here with, let's say, the digital output of a 3.3 volt microcontroller, that's huge. That's huge. Yeah, just something to keep in mind. Also here on the internet, when explaining certain circuits with TRIACs, often they say, okay, as soon as the TRIAC gets into its conductive state, gate and main terminal 1 are basically shorted out. And that's simply, it's not true. It depends on the quadrant you're in, again. And it can vary from a slight increase of the voltage drop across the gate to really more than shorting out. I mean, we have a negative voltage here. That is, that gate is sucking out more current here. Well. Let's move on to the next two parameters, the latching current and the holding current. These are currents flowing between main terminal 2 and main terminal 1, so in your load circuit. And the latching current has to be applied while you apply the gate trigger current. So you need a minimum current into your main terminal 2 to get the whole thing latching into its on state. While the holding current is the current you need to maintain into main terminal 2 to keep that thing in its on state when the trigger current is no longer applied. And as you can see, the latching current again is dependent on the quadrant you're operating the TRIAC in. But this time it's a little bit different. Okay, in quadrant 1 you have 3.2 milliamps, 260 milliamps, 4 milliamps, 5.5 milliamps. Typical. And this time, obviously, quadrant 2 is the worst. Quadrant 1 is still the best. So let's measure quadrant 1 and quadrant 2. So I wired everything up for quadrant 1. I'm not using my electronic load here. It's just used as binding posts. The current into main terminal 2 is controlled by that resistor and that potty, and it's currently at 2 milliamps. And my gate is constantly supplied with some current. And at 2 milliamps, if I disconnect the gate, it's off. So let's go to 3 milliamps.
Off. 4 milliamps. Off.
5 milliamps. And it stays on. Okay, so quadrant 1, 5 milliamps. I rewired everything for quadrant 2. That means I just changed the polarity on our gate. And at 10 milliamps, that thing won't hold.
Okay, let's try. Yeah, whatever.
12 milliamps. Oh, and it latches. Okay, I guess we have to go back to 11 milliamps.
and see if it holds there.
11, close enough. Yeah, so 11 milliamps is the latching current in quadrant 2. And while we are at it here, I'm now turning the current back. Yeah, we have no longer any connection to the gate. Gate is floating. Better put that somewhere. And now we decrease the main terminal 2 current slowly.
So 7, 5, 7, 6, 5, 6, 5, 5, 5, still conducting.
4, 5. And yeah, let's call it 4 milliamps, okay? So our measured values for the latching current were, yeah, about in the order of magnitude of the typical values. So 3.2 milliamps versus 5, 16 milliamps versus 11. But important to see, there is a huge difference between quadrant 1 operation and quadrant 2 operation. Our holding current was spot on with the typical value of 4 milliamps measured at 4 milliamps. So we have now to look at these referenced figures, because the thing is, a TRIAC is a very, very temperature sensitive device. If we look at that figure for the gate trigger current, it's temperature versus relative gate trigger current. So the values at the front of the datasheet are always given for 25 degrees C. And we see at room temperature, the factor is 1. Yeah, what we expect, because the values were given for 25 degrees C. But if we heat the TRIAC up to 125 degrees, we only need half of the gate trigger current. And since a TRIAC is also some kind of not really the right word, but bipolar device. Yeah, you know that from bipolar transistors, thermal runaway. The hotter they get, the better they work. But when it gets cold, we run into slight problems. Let's assume you want to use a TRIAC in an outside floodlight controlled by a motion detector or something like that. That curve 1 and that numbering here doesn't correspond to our quadrants. Curve 1 corresponds to our fourth quadrant, our worst case. At minus 25 degrees C, you need to apply double the trigger current to get that thing on. Yeah, and even our best case quadrant 1, you need about 1.5 times the trigger current at minus 25 degrees. So there is a huge temperature differential. If you look at the latching current, at least we only have to look at one curve. It's also relative, so minus 50 to 150 degrees C, and the relative current to the current specified at 25 degrees C. About the same. For 125 degrees C, we need only apply a little more than half, but at minus 25, we need to apply 1.5 times the current. And these are the figures for the holding current and the gate trigger voltage. And yeah, they basically show the same. Your holding current at 125 degrees C is about half of that at 25 degrees C and 1.5 at about minus 25 degrees C. Your gate trigger voltage also decreases when the thing gets hot. So that's at about 0.7 of the nominal value at 125 degrees C, and at minus 25 degrees C, let's call that 1.1 of the nominal value. There's also a little oddity here in the datasheet. If you look at the maximum values for the latching current, it's, depending on the quadrant, 30 or 40 milliamps. But the worst case holding current is 45 milliamps. So how can that be? Normally, the holding current is equal, for the typical values, or less than the latching current. And that's what we measured. I mean, we turned the potty up until it latched, then we disconnected the gate, and then we turned the potty down until the TRIAC gets again into its off state. Let me show you a little bit of a scribble there. So up to now we talked about static parameters for gating, latching and holding. That is, getting the whole thing from the off state into the on state. But that happens, of course, on a time scale, not instantaneously. If we just look at the lower curve here, that's our gate trigger current. So at some point, we have to apply that gate trigger current, and we have to keep it for a certain time until the whole thing is latched into the on state and holding. And this is the next parameter we will look on. That is the gating time. And afterwards, if it's holding, we can, don't need to apply the gate current anymore. Now, for the latching currents, main terminal 2, and the holding currents, we saw there are two cases. So in the datasheet, there's latching current. And of course, we have to apply that latching current during the latching. But then we have two different cases. Our holding current we need to keep afterwards, when we switched off the gate current, can be either higher or lower than our latching current. So, and the lower case, let's say that's that dotted line, we measured that. So, at some point we applied our latching current and kept that current, kept that constant, and we switched off our gate current, and then we could go down quite a bit with the current, with a holding current through main terminal 2, and it still held until we fell below that holding current at some point, and then we were back in the off state. In some extreme cases, as we've seen in the datasheet, your holding current can be bigger than your latching current. That is, during the time you need for latching, you have to ensure that the current through your main terminal 2 increases from the latching current. Yeah, we start with the latching current until it reaches the holding current at the point of time when we no longer apply any current to the gate. Yeah, I guess at that point it's time to get out the oscilloscope and have a detailed look at what's happening during that latching. And yeah, what that parameter TGT is all about. And here we are. So what I'm measuring here, my power supply and 9-volt battery have been replaced by channel 1 and channel 2 of a function generator. The light bulbs have been replaced by a 100 ohm resistor, and that resistor is now also 100 ohms. And I connected my channels 1 to 4 here, 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 and here. Currently, I'm also calculating the difference between channel 3 and 4, which of course gives me the voltage drop across that resistor and therefore the gate current. So I'm feeding to my main terminal 2, that is the resistor before it, a positive square wave with a duty cycle of 50%. And to my gate, a square wave, also purely positive, with a duty cycle of 10% with a little offset to my main terminal 2 square wave. And what we can see here, we are in the off state. The voltage to main terminal 2 rises, and then the trigger impulse is applied. And then we have a voltage drop here, which is not the 100 ohm resistor. That probe is just before it. That is the drop across the 50 ohms output impedance of the function generator. And then my square wave returns to 0, and my TRIAC goes back into the off state until the cycle repeats again. Now let's zoom in a little bit. So on the left, I'm in the off state, then my trigger pulse is applied, and here on the right, I'm in the on state without any trigger pulse. Forget for the moment about these two curves. These are the probes directly left and right to the gate resistor. That curve here is actually the difference of these two, and it indicates the actual gate current. So we are in the off state, we apply the gate current, and our TRIAC turns on. But as you can see, it doesn't turn on instantly. It's a process. And from the time scale here, it needs about, let's say 2 microseconds. That's a 10 kilohertz square wave. About 2 microseconds to turn on. What we can also see here, we're here in the off state, and my gate voltage, that curve here is actually the blue one is the voltage directly at the gate. It's 0, then we apply the pulse, so it gets to some defined value, but it doesn't return to 0 when we stop applying the gate voltage through the function generator. it stays a little bit up. And further down the timeline, here we switched on, you see that the voltage across the gate is only slowly creeping down and still staying above 0. And only when the TRIAC switches off, it truly returns to 0. And that's actually what we measured. So you remember when we measured the static characteristics just using the power supply and the battery, and we were working in quadrant 1, our gate voltage increased from 0.6 volts to 0.7 volts when the TRIAC actually turned on. And that's exactly what we are observing here. So you have actually a voltage coming out of the gate when the TRIAC is in its on state. And here it gradually decreases with some time constant. At that scale, 5 to 10 microseconds. Let's say here while it's on, 10 microseconds. And then when it's finally going back into its off state, it also takes a while to go down. So there's actually current coming out of your gate. But let's have a closer look here at this gradually switching on of the TRIAC. And I will now use the calculation function to actually display the current through main terminal 2. So here we are still in the off state, and these are the two probes across the gate resistors. So here comes our gate triggering pulse. These two probes are across the main terminal 2 resistor, and that curve is the difference between the two. That is the current through our main terminal 2. And you see, when the trigger pulse comes, it rises really gradually. And we've seen it before, but this is a good, 1, 2, 3 microseconds, 2 to 3 microseconds until it reaches its maximum. Now, what happens if we decrease the duty cycle of our trigger signal? Let's try that. Now you can see where the trigger signal actually ends. Trigger signal is now only 4 microseconds. It's still working. 3 microseconds is still working. 2 microseconds, still working. 1 microsecond, it's still working. 0.9, 0.8, and you see it has a little bit of problems latching onto the on state. And if our trigger pulse gets too short, now it's really struggling. Now we get some weird effects. And now, we are now at 0.3 microseconds. And the trigger pulse gets too short to get the thing reliably in the on state. And even if it's 0.4, that's not a nice switch on. 0.5, 0.6, 0.7. Okay, then it's getting better. Now, this is actually a parameter in the datasheet. And it's called the gate controlled turn on time, TGT. And yeah, for different conditions, I mean, we are not running it at 800 volts, but more like, I think, 5 volts, and not at 20 amps, but at a few milliamps. And also our gate current is, in the milliamps range. Doesn't matter. It says typically 2 microseconds, and we've seen it. It fires how we driving it at 1 microsecond pulse duration perfectly. And when you then go down below 0.5 microseconds, it really starts to struggle. And below 0.4, it cannot latch on anymore. And that's exactly our last parameter that characterizes the gating, latching, and holding of the whole thing. And if you look into a datasheet, they make up the majority of the normal characteristics of a TRIAC. There are 1, 2, 3 left, and we have to have a look at the thermal characteristics and the limiting values, that is how not to destroy our TRIAC. But I guess I leave that for 1 or 2 more installation in this mini-series. Until then, bye.